Okay, so in the last video we came across this quotient ring. Towards the end of the video, this quotient ring where Q is the field of rational numbers and where A is the principal ideal generated by the polynomial x cube minus 2, where x cube minus 2 is a polynomial over the field of rational numbers. Now here we mentioned that this polynomial is actually irreducible over Q, so that this ideal is a maximal ideal, and as a consequence this quotient ring is a field. But we only mentioned irreducibility of this polynomial, we did not prove it. So the fact that this ring is a field is still unproved in that sense, because we haven't proved irreducibility of this over the field of rational numbers. We will do that after the things are over, after the text part of this section is over, we will do that. But can we directly show that this ring is a field? In fact we can, and that's what we are going to do. So to show that this quotient ring is a field, what are the things we need to show? The first thing is that we need to show that this is a commutative ring. The second thing is that it must have a unit element that is different from the zero element. And the last thing is we need to prove that every non-zero element in this ring has a multiplicative inverse also in the ring. Now this quotient is clearly a commutative ring because it has come from a polynomial ring which we know is commutative. And there is a unit element. The unit element is just this coset 1 plus a, where 1 is the constant polynomial obtained from the rational number 1. And we know that this is not equal to the zero element of the ring, which is the ideal A itself. So the only thing we are left to show, to prove that this is a field, is that every non-zero element has a multiplicative inverse in the ring. Okay, now in that direction we are going to use something which we have already seen, which we have already found out, namely that any element in this quotient ring can be expressed in this form: a0 plus a1t plus a2 t square, where a0, a1, a2, these are rational numbers, and where t is the coset x plus a. Okay, and in this now it is very easy to lose track of what is going on here and merely thinking of this as a polynomial in t. Yes, it is a polynomial in t, but there is something that we need to keep in mind. We should not forget this. T is a coset of a, fine. A1 is a rational number. So can we multiply t by a1 to form a1t? And if so, what is the definition of this multiplication? Because we know only of two operations in this ring: one addition of two cosets and the second is multiplication of two cosets. This, however, is not a product of two cosets. It's a product of a coset and a rational number. Does it make sense? It makes sense only when you also recall that we were able to find an embedding of the field of rational numbers into this quotient, and the specific embedding was this: if R is a rational number, then its F image is the coset R plus A. The fact that this function is an embedding tells us that whether we treat a1 as a rational number or as the coset a1 plus a, it does not matter, because elements like this in this quotient behave just like the rational field because they are isomorphic. So that's why the true meaning of this expression lies in this identification, that a1 is really a1 plus a. So that's why this product is actually a product of two cosets and things make sense. Okay. Now in showing that any arbitrary non-zero element here has a multiplicative inverse, we are now going to make use of these expressions. One more thing is that for a given element, this a0, a1 and a2 are unique. Okay, we are going to make use of that uniqueness also. That is, this expression is unique for a given element. So we start like this. Let a0 plus a1t plus a2t square be non-zero, and let this be any element of the quotient. We want a multiplicative inverse of this element, which should be here, so it should also be in this form. So we want an element, say alpha plus beta t plus gamma t square, again in this ring, such that the product of these two elements and alpha plus beta t plus gamma t square is equal to the unit element in this, which is 1 plus a. Now if you go to if you go back to the previous video and you look at how we found these coefficients a0, a1 and a2, you will see that for this particular coset, those coefficients are 1 plus 0t plus 0. The coefficients are 1, 0 and 0. Because the left hand side is an expression like that, so we want the right hand side also to be in that form. Okay, so we want this to happen. The question is, does it really happen? We need to show that this happens. However, we can simplify this and we find an equivalent condition in place of this equation. So what we do, we multiply the terms out. Doing so gives us a0 alpha plus a0 beta t plus a0 gamma t square. Then we multiply by a1t, so a1 alpha t plus a1 beta t square, a1 beta t square plus a1 gamma t cube plus, then we multiply by a2 t square, a2 alpha t square plus a2 beta t cube plus a2 gamma t to the power 4. Okay, now what about t square, what about t cube and t to the power 4? You recall that for this particular element, we proved this also. Now here also, this 2 actually is the coset 2 plus a. However, you can think of it as the rational number 2 also. It does not matter because of this embedding. So that means in place of t cube we can write 2. Doing so gives us a naught alpha plus a naught beta t plus a naught gamma t square plus a1 alpha t plus a1 beta t square plus 2a1 gamma plus a2 alpha t square plus a2 beta. In place of t cube we write 2 plus in place of t to the power 4 we can write 2t because t cube times t. So plus 2a2 gamma t. This is equal to 1 plus 0t plus 0t square. Now we arrange the terms like how we have on the right hand side. We collect like terms. So first we have terms which are devoid of t, which have no t. So this is a naught alpha, this one plus 2a2 beta plus 2a1 gamma plus then terms which have only one t, that is terms which have t. So plus a1 alpha. We are also not collecting the term, we are not writing the terms after collecting them randomly. We are writing them as combinations of alpha, beta and gamma, where the coefficients are a0, a1 and a2. Some multiples of them. So this is a1 alpha plus a0 beta plus 2a2 gamma t plus then finally terms with t square. So where do we have alpha? We have alpha t square here. So a2 alpha plus then beta t square, a1 beta plus then gamma t square, a0 gamma t square. Now the fact that these expressions are unique for a given element, such an expression which equals that element is unique, it has unique coefficients. From that uniqueness, this equality or this equation is equivalent to the fact that the corresponding coefficients are equal. Since the expressions, if I write the expressions are unique, then it will not look good or it will not convey the actual message that I am trying to write. So we can write like this: from uniqueness of the expressions, say, what should I write, alpha, beta, gamma. So let me take delta naught plus delta 1 t plus delta 2 t square the above equation is equivalent to the following equations. To the following system of equations. A1 alpha plus, oh no, this one comes first. A0 alpha plus 2A2 beta plus 2A1 gamma is, that is the constant term, equal to 1. Then A1 alpha, A1 A0 and 2A2, A1 A0 and 2A2, this is equal to 0, and finally A2 A1 A0. Or we can write this system of equations. These are treated as equations in alpha, beta and gamma. In the matrix form, A0 2A2 2A1 A1 A0 2A2 A2 A1 A0. This is equal to 1 0 0. Now if it happens that this matrix is non-singular, that is if it has an inverse, then clearly we can this may be a little confusing, because this alpha, beta and gamma are things which, whose existence we want to prove. So you can think of these alpha, beta and gamma as variables, some things that we want to find out. So so this can be considered as a system of equations in these variables alpha, beta and gamma. So in matrix form, we have a single matrix equation like this. Now if it happens that this matrix is non-singular, then we can multiply on both sides from the left by its inverse and find a solution for these elements alpha, beta and gamma, these rational numbers we can find. The question is that possible? So far we have only reduced the condition that we want to be true, namely that there is a multiplicative inverse of that non-zero element that we have chosen. That boils down to showing that this system of equations has a solution. Now it is a fact which we are now going to show that this matrix is indeed non-singular by showing that its determinant is non-zero. Okay, so let us write those things. If the matrix of coefficients above is non-singular, then the above system has a solution. We will now show that this matrix is non-singular by calculating its determinant and working with it, showing that the determinant cannot be equal to 0. The determinant of the above matrix is, let's calculate its determinant, which whose formula we already know from our school courses. So it is A naught times the cross product of these two things, A naught times A naught, that is A naught square minus 2A1 A2. Then this element minus 2A2 times this minus this times this. That is the element by which you are multiplying. You have to remove the row and column containing that element from the matrix. Whatever you are left with, its determinant has to be written along with that other number. So the determinant of that matrix, that is A1 2A2 A2 A naught, is A1 A naught minus 2A2 square. Okay, so that I can write here itself. Then plus this one. This element is 2A1. So you remove this row and this column, so you are left with this submatrix. Its determinant is A1 square minus A naught A2. Okay, so this becomes, if we simplify, A naught cube minus 2 A naught A1 A2 minus 2 again A naught A1 A2 plus 4A2 cube plus 2A1 cube minus again 2A naught A1 A2, and this can finally be written like this: A naught cube plus 2A1 cube plus 4A2 cube minus 2, so that gives us 6 A naught A1 A2. So this is the determinant of the matrix. We want to show that this determinant is non-zero so that we can solve this equation. To the contrary, suppose that this is equal to 0. So essentially we are supposing that this matrix is having a zero determinant, that is, it is singular. Suppose A naught cube plus 2A1 cube plus 4A2 cube is equal to 6A naught A1 A2. Now recall how we chose the element, this element A naught plus A1 t plus A2 t square. That is a non-zero element in our quotient ring. So that means from uniqueness of that such an expression, at least one of the coefficients must be non-zero. So we can write like this: since a0 plus a1t plus a2 t square is not equal to 0, at least one of a0 or a1 or a2 is non-zero. Okay. Now we can assume that a0, a1 and a2 are integers. Originally a0, a1 and a2 are rational numbers, but we are saying that we can assume them as integers. Why? What is the justification for that? If they are non-integral rational numbers, then you look at this equation, you can each one of them will be of the form p divided by q, where p and q are integers and q is not equal to 0. So after taking LCM, after taking cubes, then taking LCM, on that side also we will do some things, and after simplification you will see that you are ending up with an equation like this, where in place of a0, a1 and a2 you may have some other numbers, but those numbers will be integers. Okay, so that's why we can assume without loss of generality that these are integers using the equation plus 4a2 cube is equal to 6a0, a1, a2, we can conclude this. I urge you to actually do it. Okay, you actually take, say, a0 equal to q0 divided by, or p0 divided by q0, a1 is p1 by q1 and a2 is p2 by q2. Substitute those expressions in this equation, then do all that simplification and see whether you again come up with an equation of this form, where the resulting numbers that you have in place of a0, a1 and a2, they are integers. Okay, that I leave to you. So now without further ado on this matter, we now assume that a0, a1 and a2 are integers. So the fact that at least one of them is non-zero continues to be true. So not all of them are 0. So that means their greatest common divisor exists. This greatest common divisor is not the greatest common divisor of 2 integers, but rather 3 integers, whose definition is also just like that one for 2 integers. It's a positive integer that divides all the 3 integers, and if a positive integer divides, or if an integer, a non-zero integer divides these 3 integers, then that non-zero integer also has to divide this positive integer. such a positive integer will be called the greatest common divisor of these three integers. Such a thing exists because at least one of them is non-zero. Okay, it's a fact from number theory. So D, which is the GCD of A0, A1 and A2 exists. Let A0 be equal to A0 prime D, A1 be equal to A1 prime D, and A2 be equal to A2 prime D. Since D is the GCD, so D will divide all these numbers, all these integers. So each one of them will be a multiple of D1 for some integers A0 prime, A1 prime and A2 prime, where are integers. We also know that these are not just integers, but they don't have any common divisor among them other than 1, no positive common divisor. That is because whatever common divisor we had among all of them, that has been taken out. I mean, among A0, A1 and A2, we have taken all the common divisors out, and that common divisor, the greatest common divisor, there is nothing greater. So when that part is removed from all the numbers, whatever is left has no common divisor other than 1, I mean no positive common divisor. Okay, note that A1 prime and A2 prime have no positive common divisor other than 1. Okay. Now from the equation A0 cube plus 2A1 cube plus 4 A2 cube equal to 6 A0 A1 A2, we see that A0 cube is even. It's an integer, so as an integer it's either even or odd, but we see that A0 cube is this minus this minus this, each one of them is even, so the linear combination is also even, and hence A0 is even. The conclusion that evenness of A0 cube implies that A0 is even is easy to justify. If you take the cube of an odd integer, say 2k plus 1, if you take its cube, what will you get? 2k whole cube, so that is 8k cube plus 3 times 2k whole square, so that means 12k square plus 3 times 2k, so 6k plus 1 cube. So you see that this is xk square plus 3k plus 1, 2 times some integer plus 1. So taking the cube of an odd integer, you again get an odd integer. So because this cube is even, a naught must be even. Let a naught be equal to, say, oh, I forgot to say one thing. No. That's how we are not supposed to solve this problem, other than from the equation. No, I forgot to use a naught prime, a1 prime and a2 prime entirely. In this equation, if you substitute these expressions, what will you get? A naught cube, okay, let me just write. We get d cube a naught prime cube plus 2d cube a1 prime cube plus 4d cube a2 prime cube. This is equal to 6d cube a naught prime a1 prime a2 prime. So you can cancel d cube from both sides. It's anyway a positive integer, that is So with this equation, we are now going to do what we were doing there. Note that this last equation implies a naught prime cube, because we have already discussed the thing once prematurely, so we don't have to elaborate on this. That means this is going to be even, and hence a naught prime is even. This is even, and so a naught prime is even. Let a naught prime be equal to 2 times, what should I take? Let me take u, where u is an integer. Then now substitute for a naught prime here in this final equation. Then if we do that, we will get 8u cube plus 2a1 prime cube plus 4a2 prime cube equal to 6 a naught prime. Oh, here also we have to substitute for a naught. So this will give us 12 u a1 prime a2 prime. Now dividing both sides by 2, we get, or 4u cube plus a1 prime cube plus 2a2 prime cube. This is equal to 6u a1 prime a2 prime. Now this last equation again implies that this time a1 prime cube is even, because all the remaining terms are even. A1 prime cube is even, and so is A1 prime. let a1 prime be equal to 2v, where v is an integer. Then now if you substitute this one in the last equation, what will you get? 4u cube plus 8v cube plus 2a2 prime cube. This is equal to 12uv a2 prime, or again divide both sides by 2. So doing that we get 2u cube plus 4v cube plus a2 prime cube. This is equal to 6uv a2 prime. Once more we repeat this process. The last equation implies a2 prime cube is even, and so is a2 prime. Let a2 prime be equal to 2w, where w is an integer. Okay, but we need not go any further. We have achieved what we want, which is a contradiction. You see, we have proved that a0 is even, a1 is even. See here, a0 prime is even, a1 prime is even, and a2 prime is also even. All of them are even. So that means all of them are divisible by 2. However, here we have this fact that they have no positive common divisor other than 1. However, we have got the positive common divisor 2. So this is a contradiction. Thus, 2 is a positive common divisor of a0 prime, a1 prime and a2 prime, a contradiction. So our supposition is wrong. What was our supposition? Our supposition was that determinant is 0, so it cannot be 0. So the determinant is non-zero, consequently the matrix of coefficients is non-singular, and that's why we are able to find a solution. That solution will give us the inverse of that element, which we chose to be any non-zero element in the ring. So we can write like this. Thus, taking, should we say taking everything into consideration, or tracing our way back, we conclude that a0 plus a1t plus a2t square has a multiplicative inverse. Alpha plus beta t plus gamma t square in our ring. So that's why this ring is a field, and in doing so we did not use the fact that x cube minus 2 is irreducible over q. Although once you have that fact, then concluding that this is a ring is just a matter of applying the previous results. The ideal it generates is maximal, and hence the quotient ring is a field. Okay. So the text part of this section ends here. Let us now look at some of the first few exercises. Now before we go to the actual exercises, I have some special exercises here which will help us tackle the actual ones. But even before that, I need to refill. So here the section on polynomial rings ends, I mean this section at least. So here the first special exercise. It's nothing very difficult or fancy, it's just a fact which is easy to guess and also easy to derive. So let's just do that. Prove that the units in the polynomial ring fx, where f of course is a field, are precisely the non-zero constant polynomials. That is, as a ring which has a unit element, the unit element of course is a unit, it has a multiplicative inverse, but there may be other elements which also have multiplicative inverses, that is, which are also units. So we have to prove that the units in this ring are precisely the non-zero constant polynomials, that is, elements in f considered as polynomials. Okay, so the solution goes like this. Any non-zero constant polynomial in fx is clearly a unit. Why such a statement without any justification? Because the justification is very easy and we can look at it like this: for any non-zero field element we have C inverse equal to C inverse C equal to 1. And since we can think of these constants C and C inverse as polynomials in fx, that is constant polynomials, so as elements in fx they are invertible, that is they are units. That's why we say any non-zero constant polynomial in fx is clearly a unit. Conversely, let fx equal to a naught plus a1x plus a2x squared etc. plus anx to the power n in fx be a unit. We have to prove, so this is a general polynomial which we are assuming to be a unit in fx. We need to prove that this is a non-zero constant polynomial. Then that means it has a multiplicative inverse. Then there exists some polynomial gx. In general, the polynomial which is the multiplicative inverse of this one will be in gx. We don't know what its degree is or what its properties are, but there is one such element in gx, so that if you take the product of this one fx and gx, you will get the unit element of fx, which is the constant polynomial 1. Okay, so there exists gx, which for which also we take one expression like this. Where it will end we don't know, so we consider it to be some non-negative integer n, bn x to the power n in such that fx times gx is equal to 1. Okay, fx times gx is equal to 1. If we assume that an is not equal to 0 and bm, here also I considered n, no, let us take m here, bm also to be non-zero, so that degree of fx is n and degree of gx is m. I mean, they will have some degree, right? This is a unit, so by definition, since it's a unit, it cannot be equal to 0. So it will have some degree. As a non-zero polynomial, it will have some degree. At the same time, since gx is the multiplicative inverse of fx, that is their product is equal to 1, so gx cannot be equal to 0, because if that is the case, then 0 will be equal to 1, which is false. In any ring, in any field, 0 is not equal to 1. Keep in mind that this 1 and these things, these are not ordinary real numbers or anything like that. They are general field elements, because our field is completely general. However, in any field, the 0 element is never equal to the unit element. Okay, so gx is also non-zero, so gx will also have some degree. So we assume that their degrees are n and m respectively. Then 0 is equal to what? 0 is the degree of the constant polynomial 1, but 1 is equal to fx times gx, and here we are able to use that degree formula. That is, if you take the product of two polynomials, then the degree of that product is equal to the sum of the degrees. Then this is equal to degree of fx plus degree of gx, and that is equal to n plus m. Now, as degrees, n and m are non-negative integers and their sum is equal to 0. So the only choice is that both of them are equal to 0. If any one of them is positive, then the sum can never be equal to 0, because there is no question of having any negative and cancelling it with a positive to give you 0. That provision is not there. Since both n and m are non-negative, we must have this. The point to be noted here is that n is 0. Now when n is 0, that means fx is equal to a naught, that means fx is a constant polynomial, and since fx is a unit, so a naught cannot be equal to 0, so fx is a non-zero constant polynomial. This shows that fx is equal to a naught. Also, since fx is a unit, a naught is not equal to 0. Thus, this is a non-zero constant polynomial. So this proves that the only units in any polynomial ring are the non-zero constant polynomials, or loosely speaking, the field elements themselves. That is polynomials of degree 0. Okay, so the next one is that claim that x cube minus 2 is irreducible over the field of rational numbers. Let me call this verify. This is something which is not there. These things are not there in the text. I added them as extra material for our benefit. Verify that this polynomial is irreducible over the field of rational numbers. Okay, here the procedure is to assume that no, it's not irreducible, that it has a non-trivial factorization in qx, in the polynomial ring qx, and then arrive at a contradiction. So that's what we are going to do. Suppose x cube minus 2 is not irreducible over Q. Then there exist some rational numbers A, B, C, D, E, where A and C are non-zero, such that x cube minus 2 is equal to ax plus b times cx square plus dx plus e. But why? How are we concluding that non-irreducibility of this polynomial over Q implies existence of these things? Note that your assumption that x cube is minus 2 is not irreducible implies, by definition, what does it say? It says that x cube minus 2 can be written as a product of two polynomials such that both of them are non-constant polynomials. That means each one of them has degree greater than 0. If you, for example, if you say, since we are talking about this polynomial, say you are able to express it only as a product of two polynomials when one of them is a constant polynomial and the other is, of course, a non-constant one, because the degree has to be 3, then x cube minus 2 is irreducible by definition of irreducibility. So from that definition, assuming that this is not irreducible gives us two polynomials, none of which is a constant polynomial. That means each one of them has degree greater than 0. Now what can those degrees be? Those degrees can be either 1 or 2. Note that if, say, fx is of degree 3, then gx must be constant, because the sum of the degrees should be equal to 3 according to that formula. But that's what we are saying, this factorization is not one like that. Here none of them is constant, so that means the only possibility is that one of them must have degree 1 and the other one must have degree 2. So we assume we assume that this is the degree 1 polynomial and this is the degree 2 polynomial. Now saying that the polynomials are of this form is not enough. For this to be of degree 1, a has to be a non-zero constant, non-zero rational number. Like that, for this to be of degree 2, c has to be a non-zero rational number. So that's why we have these things. Okay. Now if you multiply both the sides, collect like terms and then equate like coefficients, you will end up with these things. These equations, which is somewhat easy to see. If you see, AC is the coefficient of x cube. Here the coefficient of x cube is 1, so AC must be equal to 1. So you will get equations like this, or relations among these rational numbers a, b, c and d, like this. AD plus BC is equal to 0, then AE plus BD is equal to 0, and finally BE is equal to minus 2, which you can see from here. BE is the constant term. Okay, now using these things we can arrive at a contradiction. The path is a little, you cannot see it immediately. Once you see the calculation, you will understand why we are carrying out these particular calculations. A square D plus B is equal to, you can write it like this, A times AD plus B divided by A. Clearly this is equal to this provided A is non-zero. A is non-zero because that's how we chose A. Now look at this one. AC is equal to 1. So that means 1 by A is equal to C from this equation. So in place of B by A, we can write BC. Okay, 1 by A is equal to C. We get that from this equation. But this one says that AD plus BC is equal to 0. So this gives us A times 0, which is equal to 0. This is one relation that we will use. And like that, minus 2A plus B square D is equal to, you can take, see, in place of minus 2 you can write BE, right? And then you can take B common out. So let's just first write that BEA plus B square D. Now if we take B common out, we are left with AE plus BD. Again, you see AE plus BD is equal to 0. So this is equal to 0. Okay, so now what do we get from these two relations? A square D plus B is equal to 0 and minus 2A plus B square D is also equal to 0. Thus 2A cube plus B cube, okay, this can be written like this, minus A square times minus 2A plus B square D plus B square times B plus A square D. Minus A square times minus 2A square gives us 2A cube. B square times B gives us B cube. And minus A square B square D plus A square B square D, they cancel out. So this calculation is correct. Okay, now this thing is equal to 0, we have that, and B square, B plus A square D is also equal to 0. So that means this is equal to 0. Or if you write it slightly differently, you will get this. B divided by A whole cube is equal to minus 2. From this equal to 0, we can conclude this, keeping in mind that A is non-zero. Since B, A, these are all rational numbers, so the quotient is also a rational number. Since this is a rational number, we can assume So now I think now you can probably see what we are going to do here. Since we are trying to get a contradiction and we have the fact that the cube of a rational number is equal to -2, we will try to show that that gives us a contradiction. So what I am trying to say here is that if you know about the proof that square root of 2 is irrational, the standard one, there are many proofs of this, but the standard one which goes something like this, then you have probably already guessed what we are going to do here. Here however we have cube root of -2, not square root of 2. So we can assume b divided by a equal to p divided by q, where p and q are integers, q is not equal to 0, and this condition is important, p comma q is equal to 1, where you know from our notation that this is the greatest common divisor of p and q. The thing here is that if you are writing a rational number, say as a ratio of two integers, this is a rational number, then you can always cancel the greatest common divisor of these two integers, the numerator and the denominator, to ultimately end up with an expression where the numerator and denominator have the greatest common divisor 1. In this case that is not 1, that is what? 6. 6 is the greatest common divisor. 2 times 6, 3 times 6. But after you cancel 6, you get an equivalent expression for the same number like this, 2 divided by 3, and 2 and 3 are relatively prime. So we can always find an expression where the numerator and denominator are relatively prime. If they are not, we cancel the common factors that are greater than 1. Okay. Then if we substitute these things here, then we will get -2 or p cube equal to -2 q cube. Thus p cube is even and so is p. Now you know why p has to also be even. The cube of an odd integer is odd. So let p be equal to 2 alpha, where alpha is some integer. Then 8 alpha cube, I hope we haven't used alpha here. No, 8 alpha cube equal to -2 q cube, or q cube is equal to -4 alpha cube. This implies not alpha, I want q. Q cube is even and so is q. So p and q are both even, that means both are divisible by 2, but then 2 is a common divisor of p and q. So how can the greatest common divisor be 1 when we have a greater common divisor? This contradicts hypothesis that this is equal to 1. So that's why our supposition is wrong. Hence our supposition is wrong. That is x cube minus 2 must be irreducible over Q. There are ways of showing that a polynomial is irreducible over a field. Not many ways, but a few ways are there. And in this form, the way we have shown this is the worst way of showing that x cube minus 2 is irreducible over Q. Why I am saying the worst way? It's because we literally started from the definition of irreducibility. We supposed that it's not irreducible, and then we did some clever calculations to arrive at a contradiction. This shows that the task of showing that something is irreducible is in general not an easy task. Which will also be clear once we start solving the actual problem from this set of exercises. So let's end the video with the solution of the first problem, then we will continue in the next video. So let us see the first exercise. So this one ends here. We already know that in a Euclidean ring, we can take any two elements, at least one of which is non-zero, and find their greatest common divisor. And we also have from the section on Euclidean rings, there you recall that we had an exercise that gave us a sort of algorithm to repeatedly apply the division algorithm to calculate the GCD. Now here in a polynomial ring, we are given two polynomials and we have been asked to find their greatest common divisor. So this is the first one. If we apply the very first, it has two subdivisions. The very first pair of polynomials produce a horrendous calculation. Anyway, there is no going around this, so I present the calculation. You can verify it yourself. Find a greatest common divisor. So unlike the ring of integers where we have sort of specialized the definition of a GCD to be a positive one. However, in a general Euclidean ring, recall that a GCD of two given elements, when it exists, is not literally unique, but two GCDs, there may be more than one GCD. In fact, there are at least two GCDs, and they are all associates. That is, if D1 is a GCD and D2 is another GCD, then there is some unit element U such that D1 is equal to U D2. I say at least two because we know that every Euclidean ring has a unit element. So if you find one GCD and the unit element is a unit, so its negative is also a unit, then what am I writing? D2 equal to minus D1, then its negative is also a GCD, but you may have more units. For example, in a polynomial ring, we have already found that all the units are the field elements. So if you find one GCD, you multiply that by any field element, you will get other GCDs, and if your field is infinite, you will get infinitely many GCDs. So find a greatest common divisor of the following polynomials. Over F, the field of rational numbers. Okay, so what are the polynomials? Part A has this: x cube minus 6x square plus x plus 4 and x to the power 5 minus 6x plus 1. And part B is easy, far easier than part A: x square plus 1 and x to the power 6 plus x cube plus x plus 1. Okay, so here is the solution. Recall the algorithm. You have to divide one polynomial by another, find the quotient and the remainder, then divide the divisor by the remainder, and keep repeating it until you get a complete division, until you get a zero remainder that you will get at some stage after finitely many steps. The first non-zero remainder is a GCD. So we carry out the divisions, and since this one has degree 5, so we consider it to be the polynomial which is to be divided by this polynomial. I carried out this calculation many times. Each time I was unable to spot a mistake, but each time I was somewhat skeptical of the calculation because of the sheer size of the remainder and the quotient. This first remainder itself starts becoming ugly, if you know what I mean. 200x square minus 65x minus 139. So if you divide this by this, you already know, you have learned in school, synthetic division. So that's what we have done here. Then this is quotient and this is the remainder. How do we know that this is the remainder? I mean, if someone does not know synthetic division, but someone has been presented with this equation, then can that person say that this is the remainder? Yes. The thing is that he or she has to verify that the calculation is correct. And then what tells you that this is the remainder? The fact that its degree, its d value in the Euclidean ring, polynomial ring, is less than the degree of the divisor. So that's why it's the remainder. So this is the first step. Then we divide this thing by the remainder, the divisor by the remainder. And I think it's better to, shall I write here? Okay, let me try. X cube minus 6x square plus x plus 4. If we divide it by this one, then we get this as the quotient. X divided by 200 minus 227 divided by 8000 times 200x square minus 65x minus 139. Both of them are minus, okay, plus, now I have to write the remainder, this second remainder. Okay, so plus minus 239 divided by 1600 x plus 447 divided by 8000. In the second step, this is the remainder because its degree is 1, which is less than the degree of the divisor, which has degree 2. And then the next one is even worse. Next we divide the divisor by this remainder. So that means 200x square minus 65x minus 139 is equal to, I better write the equality sign here, minus 32 followed by 4 zeros divided by 239x minus 3752 divided by 57121 times the divisor, which is this one. Plus the remainder, which in this case is minus, it's a constant, 7730176 divided by 57121. And finally, if you divide this divisor by this remainder, you have a complete division. Then at that step you will get zero remainder. Why? Let me just show you why. Minus 239 divided by 1600x plus 447 divided by 8000 is equal to, okay, what should I write? I am dividing by this, no? So I have to write the quotient, and the quotient is this, 57121. Now I have the facility of inverting this element in the polynomial ring, because this is a non-zero field element, so it's a unit element in the polynomial ring, divided by 7730176 times, since we are not considering the minus sign, so that means we have multiplied by minus 1 here. 239 divided by 1600x minus 447 divided by 8000. This is the quotient. multiplied by the divisor minus 77. You can now see what we have done here, divided by 57121. That is, we have just multiplied and divided by this field element plus 0. Let me write that here. So we have obtained a 0 remainder. So the previous non-zero remainder is a GCD. It looks horrible, but sometimes that's how things are. Especially there is an area of mathematics where you will come across horrible calculations, and that is numerical analysis. Pretty routinely you will have to deal with very big numbers or numbers which need many, say if you for example express this in decimal system, then you will have many digits after the decimal point. Sometimes you need to consider 5 or 6 decimal places for the sake of accuracy. Okay, we will see these things when we sometimes study numerical analysis. So here we can say thus minus 7730176 divided by 57121 is a greatest common divisor of the given polynomials. Now the answer also looks quite bad. I mean, this is the GCD. I should not say the GCD, but it's a GCD. But we have said before solving this problem that any two GCDs are associates. That means if you multiply a greatest common divisor by a unit, the result is again another greatest common divisor. You can see that you can multiply this element by its reciprocal in the field of rational numbers to have the number 1. So 1 is also a GCD. Since minus 7730176 divided by 57121 is a non-zero rational number. 1 is, because 1 is an associate of this in the polynomial ring fx. 1 is also a greatest common divisor of the given polynomials. That is, the polynomials are relatively prime. Okay, so this is the solution of part A, and part B is easy since, so here one of the polynomials is divisible by the other. Since this is equal to the other polynomial is x square plus 1, and one can verify that this is equal to x square plus 1 times x to the power 4 minus x square plus x plus 1. So a greatest common divisor of this and x square plus 1 is x square plus 1 itself. So I end the video here. The next exercise asks us to, it gives us many polynomials and asks us to prove that they are irreducible over some given fields. Okay, so I sign off for tonight, I mean in this video. So this is me, Lucifer, from a mathematical room. Have a nice night.